So let's finish chapter 6. We left off with Professor Dave talking about calorimetry. By the way, Professor Dave is not a professor. That's his, that's like a, I don't know what you call it. At worst, it's a lie, and at best, it's just a moniker of some kind. Okay, so typically, somebody dropped out and came back. That's why. Typically, when you're trying to determine heat movement in a reaction, you want everything to be isolated from the environment, from the everything else but what you choose as the actually, I'll tell you what, let's look at it this way. Remember we had, this was an isolated system and surroundings. And we had a system here, and we had surroundings isolated here. Remember, we could have three possibilities, right? This boundary between the system and surroundings could either be open, right, in which both energy, in our case, we're going to say heat, could move either direction. And matter, like mass, could move either direction. That's open. But if we restricted the mass like that, then only let energy cross the barrier, that's closed. Right? But if we said that couldn't happen, then the system is isolated. Okay, no heat in or out, no matter in or out. So we're going to restrict ourselves in calorimetry. We restrict ourselves to the system. The system is going to be isolated. So these styrofoam cups are built so that we use styrofoam because it's a very good insulator, and it keeps heat from moving in and out of the system. So we're actually focusing just on the system in our calorimeter. Right. So another way of saying that, any heat changes that occur inside the calorimeter stay there. You know, what happens in Vegas stays in Vegas. So the total, what we know as the total heat changes in a calorimeter must total to zero. Right? Because we can't create energy, we can't destroy energy. That's first law of thermodynamics. So whatever happens in that calorimeter stays in there. Now the temperature may be measured to change, but that's because we're measuring the temperature of one part of the calorimeter. So everything that happens in that calorimeter sums to zero in terms of heat. Right? So if we have one part of the system that we've identified as part 1, and we have maybe another part 2 and a part 3, and these are all together in the calorimeter, but we've identified them as this is one type of heat change, heat change, heat change. Then when we add them all together, they have to be zero. And you can go out just as far as you want to the nth degree. It can get pretty ridiculous if you want it. So any value we determine for this Q plus the value of this one plus the value of that one has to be zero. So what that tells me is that some of them might be positive and some of them be negative heat changes. So this might be an endothermic process, this might be exothermic, this might be endothermic, and the whole total has to be zero. At the end of Professor Dave's last video, I mentioned the fact that he used the way to solve these problems the way they taught me. And I've since learned a better way, and this is the better way. Everything that happens in that calorimeter must sum to zero. Now, it'll make more sense when we work a problem. Right, this is an isolated system. Nothing crosses that boundary, and everything has to sum to zero. Now the design, we use double styrofoam cups for added insulation. And we have as a practical matter, the way heat moves in and out of that system, and we know that we can't be perfectly isolated, then it probably moves not through the styrofoam, but through the lid. So if we get some exchange of heat, it happens through the lid. And the styrofoam cups and the lid and the thermometer are our calorimeter. Now this one's got a stir in it. Some of them have stirs. I tried using stirs, but some of the reactions that we investigate are corrosive. So the wires that I was using for stirring would get corroded and they would contaminate the mixture, and I just threw them out. So if we need to do any mixing, we're going to do it with the thermometer. Just be careful, and when you move the thermometer around, you can stir your mixture. But we'll talk a little bit more about that on Tuesday before the lab. Okay, so Professor Dave did mention this formula. When we're judging the heat that's moved anywhere inside the system, if we know the specific heat of the material as S, and I like to put units in there, but don't have to put a number right now, just put units so we can see, is it making sense? So the units here would be joules, right? That's a measure of energy or heat. And this one would be joules per gram degree C. Right? Some value there, times the mass, which would be in grams, right? And times the change in temperature, which would be degrees C. Okay? So, denominator, numerator. Denominator, numerator. We got joules. So it works out. That's a correct formula. We just need values for each one of these. Okay. Now, there's another way to calculate heat, and it's the one that we're going to use for our calorimeter. Remember last week, I gave you, first, before I gave you this value, I gave you this value. This is heat capacity, not specific heat capacity, but heat capacity. So this is the term that we're going to determine. That first page in the lab is determining this value for the calorimeter. Okay, and this value, heat capacity, is joules per degree C. Right, the mass is not included in here because we've seen the calorimeter is made up of several different things, like styrofoam, a polystyrene lid, and a thermometer. So if you change one of those items, you've changed your calorimeter, and this value is going to be different. But we're going to determine this one for your calorimeter on that day. And then all we need to know here then is to multiply it by measure a change of temperature, and that gives us joules or Q. Okay, for the calorimeter. So we can determine one of these Q's might be this method, and there might be a Q in here that's determined this method. There may be another one determined this method, but there should always be, for practical purposes in the laboratory, you're going to have a value here. One of these is going to be for the calorimeter. Okay. So how do we calculate delta, right? Delta is a change. Delta is always final minus initial. And in our case, it's temperature. So the final temperature minus the initial temperature equals the change in temperature. All right, so if the temperature goes from a low value to a high value, it's going to be positive change in temperature. If it goes from a high value to a low value, it's going to be a negative value. And that's where you get the sign for Q. because this is always positive and this is always positive. This value could be negative, and that will give you a negative Q. And that's where negative positives come together to make that zero. All right. Specific heat capacity, right? I mentioned there was another possibility of molar heat capacity, right? And you just substitute, the value would be different, but the units would be moles here instead of grams. So we're going to experience both of those in the lab. All right. So there's our setup. Let's look at this, try to get some intuition regarding calorimetry procedures and outcomes. We have this example. We have 100 grams of water. So we have 100 grams, 100 grams of water in this container, and it's at 90 degrees. Okay. And then we have 100-gram sample of water in another container. But it's at 10 degrees. Okay. So what would you expect to be the final temperature when you mix those together? No idea? They're the same mass. The temperature for this one's 90, the temperature of that one's 10. They should meet in the middle, because this one has a certain heat, amount of heat, and this one has a certain amount of heat. Which way is the heat going to move? From here to there. And once they reach an equilibrium temperature, the heat transfer stops. So you should expect, with equal masses and these two different temperatures, you should expect 90 plus 10 divided by 2 is 50 degrees C. We would expect this to end up at 50 degrees Celsius. All right. Now, suppose we have 100 grams at 90 degrees. This one now is 500. We can't make that assumption anymore, right? Because this one will absorb more of that energy because there's more of it. So where would we expect the temperature to end up here? Not at 50, but greater than 50 or less than 50. It's going to be less than 50 degrees C, because of that greater mass at the lower temperature. Okay, it's going to be somewhere between 10 and 50. All right, it won't drop below 10, right? Because this one's 90. So they're going to meet in the middle, but the middle for this one is going to be more toward the 10. Now, let's calculate what that temperature would be. We have an idea of where it should be, right? So our answer should be somewhere closer to 10 than 90. So let's calculate what it is. And for this question, we're going to ignore the existence of the calorimeter. Calorimeter, in reality, it contributes to the heat transfers. But in this case, for theoretical purposes, we're going to eliminate the use of the calorimeter, and we're just going to say the total here is 0. And we're going to have some heat transfer from this 90 degrees and the heat transfer from the 10 degrees, and those combined will equal 0. Okay, so what's the expression for this one? Well, we need a specific heat for water, we need to know the mass of the water, and we need to know the change in temperature for the 90-degree experiment side. Right? Now, physically, we mix these things together, right? But mathematically, we're treating them separately. Right? So this one is also for water. We'll have a different mass, right? This is the mass of the 90 and this is the mass of the 10. And then the change in temperature for the 10. Okay? So, let's see. Let me stretch this out a little bit so I have more room. So 0 equals, all right, what's the specific heat for water? They didn't give it to us. All right, so we have to look it up. All right. So we know what the question is. What's the final temperature? But we need some information that wasn't given. Right, so let me look it up. I think I know what it is, but I'm going to look it up anyway. Okay. All right. Water specific heat. Okay, that's what I thought it was. Okay, so the value here is 4.184 joules per gram degree C. Oops. Let's put it down here. I stretched it out. I should stick to my own method. 184 joules. Actually, it should be in useful information. I didn't think about that. Joule twice. Grams per degree C. Let me see. Is it? Let's be sure. I keep saying it is. Proof is in the pudding. Go. There it is. Yep. It's in useful information. So you won't have to look it up on an exam. Okay. This is the 90-degree side. What's the mass? 100 grams. What's the change in temperature? The final temperature? What is the final temperature? That's the question, right? That's the unknown. Final temperature minus the initial temperature, which is 90 degrees. And notice for calorimetry work, we don't have to change this to absolute because we need negatives in here occasionally. All right, now what's the other Q is the same value, 4.184 joules per gram degree C. This one is 500 grams. And it's also final temperature minus initial temperature, which was 10 degrees. There you go. So there's the thinking part. The rest is number crunching. Okay. So I find it's useful with these complicated, these messy equations to try to reduce them as far as possible in steps. So if we put this one over here, let's expand it some more. 4.184 times 100 is 418.4, right? Times TF minus 90. Okay. And then the other one is 4.184 times 500, which is 2092 times TF minus 10. Okay. Now we can expand this further. Right? We need this one times that and this one times that. So 418.4 times TF minus 90 times 4. Let's see. Yeah, 90 times that one. And it's a negative sign, so we're going to have a negative right here. And this is we do that again. 418.4. That's right. Okay, so this is 3, 7, 6, 5, 6. 37,656. All right, 10 times that would be 4,000. 100 times that would be 40,000. So that's, yeah, that's right. Okay. Then 2,092 times TF minus 10 times that one. So that would be 20920. Okay. Now what we want to do is combine numbers and coefficients for unknowns. So if we take this one plus that one, 418.4 plus 2,092, and that's 2510.4 times final temperature. And then these are both minus. All right, so we'll add them together. Let's see. Yes, and then 20920. And this is 58576. Okay. So now we need to get the unknowns on this side and leave the number on that side. All right, so I'm going to have to go up here. So what's the best way to do that? Well, we want to get rid of our negative signs if we can. So why don't we bring this one over here and make it positive? That's equal to 2510.4 times the final temperature. Now to get the final temperature, we divide this one into that one. So this is still the numerator. I'm doing this in nauseating detail the first time around, just so we don't lose anybody. Okay, so 58,576 divided by 2,510.4. And I get 23.3 degrees C. Okay. So our intuition was close, right? This is closer to 10 than it is to 90. And, oh, I did animate this one. Okay. So there's the setup. And then from then on, once you get it set up correctly, from then on, it's just number crunching. Well, round it off to 2. I think we're safe to round it off to 3. All right. That's 4. That's only going to give us 2, probably. It's kind of hard to tell when you don't have a value in here. So I think it's safe. 23.3 is safe as significant figures. Okay, think you could do that? Slow and easy at first until you get comfortable with it. Okay, so let me see. I don't want to run out of too much time. I should be able to set this one up pretty quick since it's going to be set up similar to the one we just did. I just have to change some of the parameters here. But again, we're going to ignore the calorimeter for now. If we get to the point, in this lecture where we need the calorimeter, I'll stick it in there. Otherwise, I'll save discussion of the calorimeter as one of our cues for next Tuesday when we talk about the actual lab. Okay, so for this one, we have a styrofoam cup with 50 grams of water at 10 degrees. So let's start over here. Styrofoam cup, right, with 50 grams of water. 50 grams of water at 10 degrees C. So we're starting off at 10 degrees C. And we have a 50-gram iron ball at 90 degrees C. So we probably stuck it in boiling water. Well, 90 degrees wouldn't be quite, it ought to be more than that even at our altitude. Anyway, this is theoretical anyhow. So we put an iron ball in here at 90 degrees C. So far, that's everything given except for specific heats for water and the iron. Okay, and the question is, what's the final temperature? Well, let's see, it's asking for intuition at first. If we have 10 degrees, notice that the specific heat, the way it's written, think of it in terms of what kind of temperature change can you expect from a certain amount of heat? If we have iron here and water here, and water has 10 times the heat capacity, the specific heat capacity is iron, then it's going to take a whole lot more heat in water to make the temperature rise. The same amount of heat that you would put in water to get it to go 1 degree, you put it in iron and it'll go 10 degrees. That's another way of thinking of specific heat. So I would expect the temperature to end up very close to the water. And that's probably here. Yeah. Calculate the final temperature. Is it animated? Come on. Yeah, there we go. So, all right, I'll do it out anyway. So we've got a Q for water and a Q for the iron. Okay. So the Q for the water is going to be the specific heat of water times the mass of the water times the change in temperature for the water. Okay. And then similarly for the iron, we have a different specific heat for iron this time. Our previous problem, we had the same specific heat for water in both circumstances. And then the mass of the iron, and then the change in temperature for the iron. Okay. So specific heat of water, 4.184. I'm going to leave the units out just for compactness. The mass of the water is 50 grams. And the change in temperature is final minus initial, which was 10 degrees. Okay. So then, I will pull it down here a little bit. Specific heat for iron is 0.45 joules per gram degree C. And then the mass of the iron is, oh, I forgot to write that in there. How big is it? Oh, it's 50 grams also. There we go. And then how does it change? Final temperature, which is the one we're after, minus initial temperature, which is 90 degrees. Okay, so now we can reduce this further. I'm going to say this times that. Take a little shortcut. So 4.184, and I'm using the 3 decimal points rather than 2 that are given there. So we'll be a little bit off from the calculation that we have here. Let's see, we've come how far so far? That's as far as we've come so far. So 4.184, oops. there we go, times 50 times TF. And that's 209.2 TF minus, and then this times 10, which will be 10 times that, only have a negative sign. 2092. Okay, that's the first part for the water. Now for the iron, we have 0.45 times 50 times TF, which is 225 TF minus 90 times that value. This value gave us the coefficient for this one, times 90 would be this value. 2025. Okay. Now we can combine these two right here. Let's see, 2092. .2, okay, and then 225. So this one's going to be 434.2 TF, and then 2092 and 2025, they're both negatives. So 2092, 2025, this is negative 4117. So if I bring that negative over here, make it a positive, then TF is going to be 4117 divided by 434.2. I skipped a step. Did you see what I did? I moved this one over here, right, and made it positive. Or in math, when they first teach you this procedure, you add 4,117 to both sides. That cancels this side and leaves it over here. So 4117 goes on this side. Now I'm taking this coefficient and dividing it into that one, and that equals the final temperature. 2. And now I get 9 point, that's not right. I got a decimal off somewhere. Yeah, there's a decimal somewhere. Let me go back. 4.184, 50. So that's 209.2. That was right. And then 10 times that is 209.2. Yep, that's right. Then 0.45 is 50. It's 225. Nope, 22.5. That's the problem. That makes this one times 90 is 2025. Okay. Now, and this one's going to be different also. You guys are supposed to catch me when I do this stuff. That's your job. 209.2 and then 22.5 added is 231.7. And 2092 and 202. No, it's not right. Is it? No, it's not right. It's 202.5. Okay. That's 2294. 2092 and 202.5. Yep. Okay. Now I can bring this one over here to 294.5 and divide it by 231.7. that's still wrong. Did something wrong again. Let's see. Yeah, I sure did. It's 209.2. Yep. And 10 times that with this, okay, that one's good. This one is 0.45 times 50 would be 22.5 times 90 would be 2025. Had it right the first time. Hope you're writing in pencil. Okay, now let's try this again. 209.2 and 22.5 is 231.7 times TF. And then 2092 and 2025 is negative 4117. Now we bring 4117. I had that right the first time. Divided by 231.7. Now we're talking 17.8 degrees C. Probably should have let the animation do the talking for me. Round it off to 18. Now, the times that I've worked that out wrong, how did I know I got it wrong? And had to go back and check it. Because the value I got was 9 something. It can't be less than 10, can it? I got a 9 down here. So they had to be wrong. It's got to be between 10 and 90. Okay. And I'm trying to make a teaching point out of this mistake. Okay, that's where I had paused in the past, but we're going to barrel on through. Okay, so if we were to conduct this in the lab, we would have another Q term out here for the calorimeter. Okay, and that calorimeter would be the calorimeter constant times the change in temperature. That's all we would add to it if we were doing it in the lab. But in either case, everything has to add to 0. Okay. Hess's law. Hess's law depends upon this one factor. Enthalpy is a state function. Delta H is a state function. Doesn't matter how we get there. It's not a path function, it's a state function. So if we want to know the delta H for any chemical reaction, if we know, and this is for the total reaction, we can find the delta H for some other reaction plus the delta H for two of them. Delta H for another reaction plus however many it takes. As long as these reactions, we can combine them into that reaction. Right? If we can take these component reactions and put them together and they come out to give us the reaction for this one, then if we know that one, that one, that one, we add them together and that gives us the delta H for our final reaction. That's Hess's law. So the advantage of Hess's law is that it isn't necessary to conduct a calorimeter experiment to determine the enthalpy of a new reaction. Right? You may eventually want to, but you can get pretty close with these different component reactions that you already know. As long as you combine them together, and we've got some rules for that. I'll give them to you in a minute. Combine all these equations, gives you this equation, then you can calculate the value that you expect. Now, the second reason for doing this is if the reaction you're investigating is likely to be extremely exothermic, like violently exothermic, even explosive, then if you know its heat output, then, and you still want to study it, then you can scale it down, small amounts, so it's containable. Right? If you don't know what the reaction is and you just throw stuff together, in large quantities, you could blow up a building. So for safety reasons, it's good to know what to expect out of a new reaction. Oh, Professor Dave's going to talk one more time.
Professor Dave here. I want to tell you about Hess's law.
He knows a lot about the science stuff. Professor Dave explains.
Thermochemical equations can be manipulated to give important data about chemical reactions. We can use them to predict exactly how much energy will be absorbed or released by a reaction, which is very important because we don't want any unexpected explosions. There are two ways we can use tabulated thermochemical data to calculate the delta H of any reaction. The first way requires that we manipulate thermochemical equations in specific ways. So let's be aware of some rules. First, if a reaction has a particular delta H, the reverse of the reaction will have the opposite delta H or the same number with reversed sign. Second, if molar quantities in the equation are multiplied by a coefficient, so is the delta H. So if you double all the substances, double the delta H. These are things we can do to thermochemical data to be able to add equations together to result in a reaction we are curious about. Here's what I mean. Let's say we want to know about the change in enthalpy associated with a reaction, like this one. But it is difficult to measure experimentally. We can take other reactions with known enthalpy changes and rearrange them to align with our equation and get the data we want. The first reaction provided has carbon graphite on the left, which is where we want it. But the equation we want has 2 moles of graphite, so let's double this one. We get 2 moles of everything instead of 1, and we double the delta H. Next, this other one has CO on the right, where we want it, and in the right amount. So all we need to do is add these equations together. The O2 and CO2 will cancel because they are present in the same amounts on both sides, and we are left with the substances in our original equation. Since we added the equations, we also add the delta H's to get the delta H for our equation. This kind of manipulation is allowed by Hess's law. We can manipulate the coefficients of a reaction or reverse its direction in any way necessary as long as we change the delta H associated with it in the appropriate way. Then we add or subtract the equations as necessary to give us precisely the equation in question. The delta H you get by doing the arithmetic will be the delta H for the reaction. Another way to calculate an unknown delta H is to use standard enthalpies of formation. This is denoted by the following symbol, and it represents the enthalpy associated with forming 1 mole of a substance from its respective elements in their standard and most stable state. Most stable state means the most common allotrope, or physical form of an element. So carbon graphite instead of diamond, diatomic oxygen instead of ozone, and so forth. Standard state just refers to standard temperature and pressure, which is room temperature and atmospheric pressure at sea level. That's what is meant by the degree symbol. We can calculate the change in enthalpy for a reaction by adding up the standard heats of formation of the products and then subtracting the sum of the standard heats of formation of the reactants. The heats of formation can be found in your textbook or online, and you just plug them in, multiplying each value by the coefficients in the balanced equation. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.
He introduced a concept that we haven't covered yet, but it's coming really soon. Let's look at Hess's law first. This particular reaction where you have N2 gas, and I call this the target equation. And this equation must be balanced before you can use Hess's law. Okay. All right. So we've got this value which is determined, and we're going to see if we can get close to that by using Hess's law and two other equations. So if we have this equation, which is nitrogen gas plus oxygen gas yields 2 nitrogen monoxide. Let's see, nitrogen gas plus oxygen gas, yields 2 NOs. And the delta H for this one is 180 kilojoules. Okay. These are both positive. So what does that say about these equations? They're endothermic. They absorb energy. All right. Then we have another one, 2 NOs. Let's see. Which is a gas. And then oxygen gas yields 2 NO2. 2 NO2. And the delta H for this one is minus 112 kilojoules. This is exothermic. So these reactions are not actually happening when you put nitrogen together with oxygen and get NO2. These reactions are not occurring, physically speaking. Right? There's a different pathway for these. But because enthalpy is a state function, we can mathematically add these together. Right? Now, if this is our target equation and these are our components, then do we have what we need? Right? We have one N2 and we have an N2 here. We have a 2 NO2 there, and we have a 2 NO2 here. Right? We have an oxygen here and an oxygen here to make 2 of them. Right? But we've got this NO. Well, it's on the product side here, and it's on the reactant side here. In the same amounts, it cancels. Mathematically, it cancels. So we can throw it out. Now, if we add these together, we get that equation. And if we add these together, we get 68 kilojoules. So that's the delta H of the combined equations. All right. That's a very simple example of Hess's law. This is another way of looking at it in an energy diagram. The y-axis is the enthalpy change, and the blue and the red lines show you the different chemical reactions. So in the one-step reaction, we go from N2 and O2 on the right, where it says red, and we move from one energy level to the 2NO2 level. It's a higher energy because it's endothermic. It absorbed energy to get there. Right. So in the one on the left, we get the first reaction, 180 kilocalories, takes us from N2 and 2O2 up to O2 and 2NO. But then if we go from this one, we add an energy here, and then we have an exothermic reaction on this side, we end up with exactly the same energy change. The enthalpy change is the same for both of them. That's the whole point of that slide. Just to show that enthalpy is a state function. It doesn't matter what the path was, because the path on the left is 2 steps. The path on the right is 1 step. All right. These are the rules, and I think Professor Dave mentioned them. If a reaction is reversed, you change the sign of the enthalpy. And if you change the molar quantities, like say if we needed to multiply this whole equation through by 2 in order for it to add together. If we multiply by 2, then we multiply this by 2. Okay. So if we look at these 2 possibilities, and notice in this case, we have fractional coefficients. Right. When we first started the balancing equations, we wanted the simplest whole number. But sometimes fractionals work better. So the top one is ammonia decomposing into nitrogen and hydrogen, and the bottom one is hydrogen reacting with oxygen to get water. And our target equation is 2 nitrogens plus 6 waters yields 3 oxygens and 4 ammonias. I'm not going to put this one on the board because it would take too much time. So I think I've got it animated. The best way to handle these types of problems is to work backwards. If this is the end result you want, look at each of the components and find them in the various equations that you're given. And then put those equations here in such a way that the component you're looking for is on the right side, and you have the same number of moles of each one. So working backwards, you go from here, and then you set up these guys to give you what you want. Reversing any reactions as necessary, and multiplying as necessary to give you the right number of moles of each reactant or product. So we need to reverse these 2 equations that we were given. So now ammonia is on the right-hand side where it should be, and oxygen's on the right-hand side where it should be, nitrogen's on the left, water's on the left, and hydrogen should cancel. Right, did we have to multiply by? Not yet. Reverse the 2 reactions first. Then we multiply by a factor to give us the right number. Let's see, 46,484. We didn't have to multiply by anything. Looks like. Oh, no, here we go. Sorry, part of the animation. So we had to multiply the top one by 4 to give us 2 nitrogens, because we need 2 nitrogens in the final reaction, and so forth. And we multiply the delta H by 4 also. The bottom one has to be multiplied by 3 to give us the correct number of waters. And then the hydrogen cancel, and we can add our values together. So we know that for this reaction, the delta H is endothermic in the amount of 1,268 kilojoules. Okay, now to the standard enthalpies of formation. Sometimes this works better. The standard, in order to use the standard enthalpies of formation, we need to start with the proper equation. So the delta H for the reaction is equal to, where's the equation? There it is. I'll come back to that. Everybody know what this sign is? Sigma. Means add everything else, add everything up that's after this. So this is for the products. Add up all of the heats of formation for the products. And we want to introduce the number of moles also, because the heats of formation are based upon 1 mole of the compound. So if we have more than one, like we have a coefficient of 2 or 3, you'd have to multiply that times each one as appropriate before you add them together. All right, I'll show you an example in a minute. And this is the heats of formation for the products. And then you subtract the heats of formation for the reactants. Delta H formation. Okay. Now, the heat of formation, this delta H of formation, is based upon the compound at 1 atmosphere pressure and 25 degrees Celsius. And if it happens to be in a solution, then you need 1 molar concentration. Now, pure substances don't have heats of formation. For instance, elements like nitrogen gas, potassium metal, they don't have a heat of formation. That's 0 because they're at their standard, most stable state. I think this is confusing. I'm going to skip this. And we use similar rules, right? When a reaction is reversed, the magnitude of delta H remains the same, but its sign changes. Let me go to an example. Yep. I mentioned this one earlier. The delta H, and that's 0. And we just use a small f, and I wrote out formation just to be complete. But for an element, the standard state, the delta H for the standard state is 0. So if you have any elements in your reaction, like this one, 2 sodiums plus 2 waters yields sodium hydroxide and hydrogen gas. And this is the aqueous. Okay. So that aqueous would have to be 1 molar concentration. This one is going to have a 0 heat of formation. This one will have a 0 heat of formation. So the only two we need are sodium hydroxide, which is minus 470 times 2. Okay. Minus 470, is that kilojoules per mole times 2 moles. Right? That's product. It's the only product we're interested in. Minus the standard heat for water. So this is 2 moles. And water is minus 286 kilojoules. Minus 286 kilojoules per mole. So moles cancel. Leaves us with kilojoules, excuse me. Kilojoules. And when we add those together, we get minus 368 kilojoules for that reaction. That's the delta H for that reaction. And that's based upon the heats of formation for each of these compounds. Now, let's see if I got a slide on it. 1 second. No, I don't have a slide, so let me show you. All right. If you're given a problem, and you need to know what the reaction is for the heat of formation, you always start with the compound. Okay. So let me see. Let me think of a simple. How about diphosphorus pentoxide? I think that's a solid. That's where you start. 1 mole of your compound, and then you work backwards. And on this side, you have oxygen. Its most stable form is diatomic gas. Right? Phosphorus, its most stable form is P4, solid. Okay? So now that we have these in their most stable form, elements, then we have to reconcile the numbers on either side. We need 5 over here. So we need a fractional coefficient of 5/2. Right? Remember that trick we use in balancing equations? Same thought. 5/2 of O2 gives you 5 oxygens. How about 4 here and 2 there? Well, we only need half of them, right? Half of these 4 gives you 2 there. So this would be the equation for the standard heat of formation for P2O5. Would be that form. And then you look it up in a reference manual and it give you a value. All right. So let's see. Pretty close to them. Oh, yeah. We're going to talk about sources of energy. This is where I get to climb up on my soapbox. About the numbskulls that support man-caused global warming. Some of those numbskulls ought to know better. Like, I don't know, Neil deGrasse Tyson he's a physicist that I'm sure he's perfectly competent in his narrow field of physics. But when you start branching out and talking about stuff you have no idea what you're talking about, then, and lots of people do that. I mean, I'm not just picking on him. It's just the fact that he knows physics. He doesn't know climate science. And I wouldn't claim to know it either. I just depend on the true experts, those people who study the stuff and make reasoned arguments. And they don't say things like settled. Let's see. Can't even spell. settled science. You know what an oxymoron is? It's a combination of words that don't belong together, right? That's what this is. There's no such thing as settled science. Science is a continuing effort to determine the truth about the natural world, right? And it's always changing. So when anybody tells you settled science, you have my permission to call them a liar or an idiot, whichever you prefer at the time. Okay. So let me get back to my slides. So what are our sources of energy, excuse me. Fossil fuels are still the main provider of energy on this planet. Fossil fuels have been responsible for pulling more people out of poverty and destitution of all kinds than any other source. Now, there are others that contribute a considerable amount. In some countries, contribute a lot. Nuclear power in some countries is almost all that they have, probably because their source of fossil fuels is limited and they don't want to import, but they do have radioactive minerals that will provide the nuclear power. But globally speaking, fossil fuels have been the biggest source of energy, at least since the Industrial Revolution started, and probably before. So we're talking about fossil means in the ground, right? So stuff that comes out of the ground that we can react, usually with oxygen, and get energy from it. Petroleum, like oil, natural gas, coal, those are fossil fuels. Before fossil fuels, our main source of energy was wood, until we cut down all our forests. We still have some hydroelectric sources that are working. The problem is that the ability to produce electricity from dammed up rivers is limited, because you only have so many rivers that will lend themselves to producing hydroelectric power. And we've dammed up pretty near all of them that we can for large scale base load production for a society. Now, there are examples, there are smaller rivers and streams that you could dam up and produce electricity for 1, 2, maybe 10 households. That's still available. And you can look those up on the, Google those and see some ingenious designs that people have incorporated into the grid, so that they can be off the grid, produce all their electricity from hydropower. Nuclear power. If we're ever going to get away from fossil fuels, nuclear power is the way to go. Now, for the present, the only type of nuclear power we have available is fission. Oops. We're working on fusion type power, but it's probably 30 years away from practical application. But we're making progress, slowly but surely. And there are several ways that we've tried to simulate the reactions that go on inside the sun or inside any star, fusing lighter elements into heavier elements and deriving energy from them. But the safety record for nuclear power is a lot better than people want you to believe. Right? We have some examples of catastrophic failures, right? The Russians several years ago, actually several decades ago, had Chernobyl meltdown and contaminate all of Europe. And that was because they were communists trying to be capitalists, and they failed. And then there was was it Fukushima in Japan, I think, where they had an earthquake and it damaged the reactor and expelled some radioactive materials.
There was a tsunami at the time as well, if I'm not mistaken.
Yes, exactly right. Yep. So you got to take into consideration where you put your power plants too. Let's see. Oh, everybody points to 3 Mile Island. Right. As soon as 3 Mile Island happened, some enterprising writer and director and producer combination in Hollywood decided they'd make a film on call it the China Syndrome. And they made a bunch of money off of it. But they didn't solve the problem. They just lined their pockets with money and awards. So the nuclear power that's being used today is much, much safer for several reasons. One is a lot of the power plants that use nuclear power as their source are a lot smaller. So if something goes wrong, the catastrophe is not as big. In fact, some of them are even portable. They put them on barges and they run them up rivers and they tie into the grid for a local area for a certain period of time, charge them money for it and go someplace else. They call them modular reactors. And the other reason that modular reactors are good is because they can be made on an assembly line, right? And they can be made really fast and under controlled conditions. So they're not one-off productions. Okay, so let me move on. Fusion power is the holy grail, right? Because it produces no radioactive waste. And if something goes wrong with any of the systems in there, all you have to do is just flip a switch or have a computer flip the switch and the whole thing shuts down. There's no chance for radioactive fuel to overheat, melt, and go through the bottom of your reactor. The whole process just shuts down. Okay. Notice wind and solar are missing. One of the primary reasons that wind and solar cannot produce baseload power for any society is that it's intermittent. Solar, obvious, right? So maximum 12 hours a day, you'll have sunlight. And that's if you don't have any rain clouds. Wind power, some places on the planet don't get enough wind to turn a turbine. Some places get a lot more. And some places are intermittent, right? So they're not reliable. And the energy that's produced by any one of these sources for baseload has to be continuous, right? You can supplement it for short periods of time with other forms of energy production, electricity production. But for baseload, wind and solar are just no-brainer. They're out. They can't do it. We can produce enough power in this country if we covered half the land mass with solar panels. So this is just a graph to show you how things progressed over time. The red is wood, right? So in the mid-19th century, we had wood was our primary source of energy. And this is on an overall scale, not like somebody's fireplace, heating their house in the winter. That's something else. This is industrial uses. By the late 19th century, wood was starting to go out and we were moving to coal. And in the 50s, we started moving more toward natural gas and oil. And these reasons are largely economic. Because with coal, well, back in around 1900, we didn't have the equipment to do large strip mines efficiently. Now we do. But when oil was discovered and natural gas were discovered, it was easy to get them. Right? All you had to do is sink a well and it just, right, it comes right out for a while. So it was cheaper. And even in the 21st century, oil and natural gas are still major suppliers of our energy needs. Only now with the advent of fracking techniques, we can go into long dead fields of oil and natural gas and rejuvenate them, because they stop producing because the rock is too dense. It won't let it come out. So we drill down, and they've got ways of drilling down and then turning and just sending a pipe out through the strata. And then you go in and you blast holes in the sides of the pipes, and then you pump it full of this mixture. They call it, I don't know if they call it drilling mud, but it's a certain mixture of things, liquids, under very high pressure, and it fractures the rock. And that allows the oil and gas to come out. So we go in and rejuvenate these fields. And we even have access to fields that weren't economic before. These rock formations that were just way too dense. It just didn't pay to go down there and drill a well because you wouldn't get anything out of it. But we knew the fossil fuels were down there. Okay. So let's start. Oh, I'm going too far. All right, let's make this quick then. The Earth's atmosphere is transparent to visible light from the sun. So visible light goes through the atmosphere, strikes the Earth. Some of it's absorbed by plants, some of it's absorbed by inorganic substances, and and some of that is re-radiated at longer wavelengths. That's typical. So that part of the warming issue is true. We do get re-radiation at longer wavelengths. So when that radiation is sent back out toward space, there are molecules in the atmosphere that will absorb that light, whereas the visible light coming through, they didn't absorb it. But as it tries to get out, it's infrared, those molecules absorb it. And there are a whole host of different ones. Carbon dioxide is blamed for global warming planet-wide, whereas carbon dioxide is only about 400 parts per million. And water is in the percent range, right? And water will absorb infrared radiation. It's not as efficient as carbon dioxide. It's not as efficient as methane either, but there's a whole lot more of it. So water is the primary source of absorption of re-radiated energy. So when you have clouds, it lets less light through, plus the re-radiation is reabsorbed. So that's the whole idea behind global warming or global climate change now. They couldn't make warming stick, so they had to call it climate change. Let's see. Oh, sorry, that's the whole thing there. Okay. The main problem is the climate was way too complex. All the models, all the mathematical models that are presented for predicting temperature change over time fail. Every one of them. None of them work. And remember when we were talking about chapter 1 or 2, I think it was, what do you do when a theory fails? Right? If your theory, the model fails, if the equation can't predict accurately the outcome, then you either restrict the application of the model, or you tweak it, right? Which is what they're trying to do with these models, but that doesn't work either. Or you throw it out and start over. And the fourth one is make a religion out of it. And that's what scientists who have a financial vested interest in global climate change, they have made it into a religion so that they can continue to make money off of it. There's one thing, I heard this explanation once before. There's one thing that the model does not predict. It has a one-way path. Light comes in at this latitude, re-radiates, in and out, in and out. The problem is the atmosphere is not static. In other words, heat that's tried to re-radiate here, it may be in water, it may be in the air, and those air masses or water masses move, right? And if they make it to the pole, there's nothing to hold them back at the poles. right? They don't have just such density of these molecules at the poles. The air is drier. The poles are not industrialized areas, so they don't have these absorbing molecules. The heat can just go right into space. So they don't account for that transfer of energy laterally on the surface of the Earth. I think that's probably the main source of failure for these models. Okay, so here's some options for the future. Coal conversion to gas, right? Takes all the ash out. It pyrolyzes the hydrocarbons down to smaller molecules that when they react, they give you the same amount of energy, but with less pollution. Hydrogen as a fuel. This is the holy grail of chemical fuels, right? The holy grail of electricity is nuclear power, fusion. But the holy grail of chemical power is hydrogen, because all you need is water and electricity, and you can generate all the hydrogen you need. We can put it in internal combustion engines with some modifications. We can put it in fuel cells and make electricity directly from the hydrogen. Other alternatives, oil shale by fracking. Get oil from really dense shale. And over the short term, over the next, say, 100 years, 200 years, fossil fuels are still going to be the primary source of energy. We can't get away from it. Natural gas from fracking also. Ethanol. The problem with ethanol is in this country, we use corn to make ethanol. It costs more in terms of energy put in to make ethanol out of corn than it does the energy you get back when you burn it. So it's the only reason that ethanol is viable in our economy, and you see 10% mixed into your gas tank, is it's government subsidized. If government stops subsidizing ethanol production, it would go away overnight. Methanol is another alcohol that we can burn, and there are various ways to produce it. Seed oil. It's funny when I learned that the diesel engine, these big trucks that run around on diesel, Herr Diesel, the German guy that invented it, used not petroleum-based products. He used vegetable-based oils, seed oils, in his engines. That was originally how it started. There's solar, photovoltaics, they call them, or wind, because winds are driven by the sun. Numerous problems with that. I've already mentioned intermittent availability. We have inefficient storage technologies. So when we're producing excess power from solar or wind, we don't have any place to store it, right? You need battery farms that are the city sized and then the battery technologies have a limited life and reliability also. Right? We hear about these cars, electric cars that burn up because of the lithium batteries that can't stand certain conditions. They've even taken down airplanes. And at present, it's not competitive. It needs government subsidies to continue. And then there are environmental hazards. Environmental hazards of producing photovoltaics on the front end are significant. And then they have a limited life. And then what do you do when you have to toss them, get rid of them? You have more contamination, usually in the form of rare earth elements. So what do? We send them to India and let kids pick through the trash and pull out parts, and then, it's morally reprehensible. And then there's nuclear power. That's the one for the future. So here's another thing you can do. if you run into a hardcore greenie who is trying to shut down all fossil fuel use and production, then ask them what their stance is on nuclear power. Because nuclear power doesn't add greenhouse gases, right? It's fairly safe now. If they're against nuclear power too, then same thing. You can call them either a liar or a cheat or whatever you want to use, because they're disingenuous. If they're against fossil fuels and they're not for nuclear, then they're lying to themselves. Okay, that's it.